and you turn it into higher molecular hydrocarbon like petroleum and so forth. Okay, and with the catalyst, you can do it at normal condition, right? Otherwise, you have to do it at really high, difficult condition, like high pressure, high temperature, and so forth. With the catalyst, you can do it at 1 atmosphere and about 200 degrees C, which is very nice, right? You don't have very severe condition. And the catalyst, why it works, you have all these catalysts, iron, cobalt, and things like that. Because it provides a different alternative site, and it provides a surface site. The key word here is surface site to allow this reaction to occur. And this is a classic example, right? Here's a table which lists how you make these Fischer-Tropsch reaction into all this hydrocarbon material, diesel, oil, paraffin, and gasoline, and things like this, right? All of these, and in fact, a lot of the work going on in the catalysis group in chemical engineering, they're still working on this. These guys are working on 20 years related to, now they're working with the tar sand people in Alberta to come up with different catalysts to refine petroleum, right? This is related to petroleum refinery. And it's a very important topic in that field. When you talk about catalysis, there are two types of catalysts. One is the heterogeneous catalyst, and the other is homogeneous catalyst. And this is all depends on whether it's heterogeneous or homogeneous. It depends on whether the catalyst is in the same phase as the reactant. Okay. So if you have heterogeneous catalysis, right, like this, your reaction occur, you have gases, right, like refining petroleum, for example. Your catalyst is usually a solid form. It may be a metal embedded in some alumina, right, in some sea life perhaps. And these are all solids, but your reactants are all gases, okay? So here catalyst is in different phase as the reactant. But a lot of the catalysis research is to come up with not heterogeneous catalysts. That's easy. That's just surface science, right? They think. The other guy, if you're a chemist, you would like to come up with homogeneous catalysis. And by homogeneous, you mean that the catalyst is in the same phase as the reactant. So you look down here. They come down, these catalyst material are usually salt or some other chemical that you can dissolve along with your reactants to give you this. So here is where biochemistry comes in. And all the enzymes, right, are catalysts, right? Enzymes, they are homogeneous catalysts because they are in the same phase. They are molecular catalysts because they grab other molecules to provide in the molecular site, right, to provide the reaction to occur. So biochemistry took over in here in homogeneous catalysis. Very, very crucial thing. And the last little bit that I want people to have some idea is oftentimes people, when they talk about catalysts, they talk about two things. And in surface science in general, you talk about reactivity versus selectivity. Right? So how fast reactivity is how fast the reaction goes. Selectivity means that what type of reaction that a particular catalyst can promote. Okay? So here you have a different reaction probability, RP reaction probability, for different reactions, you see? And they have different reaction probability like this. And they could be very selective. So here I have a whole bunch of reaction, right? Organic reaction. And I have to select my catalyst so that I only promote one of them, for example. I don't want to enhance the other reaction, right? Because I want just this product. I want an alkane product. I don't want benzene. But on the other hand, sometimes I want a catalyst that will promote just benzene reaction and not this alkane reaction. So selectivity versus reactivity is important. Not your site not just need to adapt to the particular reactant, but also need to be be selective, so that certain molecule will only fit your site, not the other, and that will introduce selectivity. So two keywords that you may encounter very often in catalysis or in service science field. And here's an example. For example, in catalysis, this is a way to look at two different type reactions. Here you may show some selectivity here, right? When you talk to catalysis people, you can see they are different by 2 order of magnitude in terms of the turnover number, right? You see, turnover number, they are different. So here you have a selectivity reaction because I can control. This one is more productive than this one. And I say, coming back full circle, I say catalyst is nano because their catalysts usually occur. The best catalysts work around 5 nanometer particle size, and those guys in ChemEng have been working on this for years. But of course, there are other nanosciences, as you guys find in your term paper, than just catalysts. But catalyst is a traditional nanosciences. And here you have surface intermediate when you're talking about catalysis, what kind of promotion that you have. And finally, you have to consider co-absorbate. And in particular, carbon, right? When you're doing a certain reaction, carbon will occur. Carbon is everywhere, it's unavoidable. And this could generate detrimental effects. So here's an example of degradation of the catalyst, right? Here's the reaction. And as your reaction proceeds, the carbon builds up and your reaction will drop. So here the carbon is a poison on your catalyst, not just poisoning your catalyst. So the kind of thing that you have to consider. Very important topic in petroleum refinery industry because sulfur is a classic poison in a lot of these catalysts. Because sulfur absorption on metal surface is very strong. Once the sulfur comes onto your absorption site, you will never be able to get rid of it. So there's a lot of work to try to avoid, try to get rid of somehow the sulfur on your poisoning your catalyst. Okay, so that's it. So I have 1 minute to spare to tell you a little bit about the final exam. The final exam will not be as, I would say the problem set sometimes is a little bit involved in terms of numbers. The final exam will have a mix of short question and simple question, right? There will be a simple question and then there will be short work. There will be choice question, it could be multiple choice type question, and then there will be short question, which are similar to your problem set, but less complicated, right? There will be some soul work question that I like people to do, right? With some simple idea that sketch derive, and not so much derivation, but using some simple equation to show me a number or something like that, some simple calculation like that, but no, essentially no derivation.